Hello, everyone. Thanks for joining us for Building Embedded Software Efficiently with an IDE, our June free webinar series. I'm your host, Teresa Kisha, and with me again today is Maciej Halasz, Vice President of Technology here at Timesys. And Maciej also heads up our EMEA office and will be the instructor for today's session. Today, we wrap up this series with session 4, Code Optimizations with TimeStorm. I have just a few notes before we begin. Once again, this event will be recorded, and following this live session, you can use this very same link to view the recording as many times as you'd like. And I will also send everyone who registered for today's session an email with a link to today's presentation so that you'll have it for future reference. And if you have any questions during this session, please use the live chat window to post your question. Once the presentation has ended, Maciej will take some time to answer any questions that we receive. And I believe that's everything. So with that, I'll hand controls over to Maciej to get things started. Thanks again, and we hope you enjoy today's session.
Thank you, Teresa, and welcome back, everyone. Today is, as Teresa mentioned, a last session in our series on building embedded software efficiently with an IDE. And today's session, we're going to focus on code optimizations. So Linux code optimizations is a topic of today. So just to recap, first session was the intro to our IDE. Then we talked about application development. We talked about system level development. Those videos are posted on YouTube channel. So if you haven't had a chance to view them prior to this session, I encourage you to take another look at them. And today we're going to talk about code optimizations. Why do we have to optimize our code? As developers, we'd like to think that whatever software we write is perfect, don't we? Well, I've been a developer at least for part of my life, professional life, and well, I know better. I know that no matter how hard I try, there's always something in a system that is going to cause potentially some problems. So why would I optimize? That's one of the questions that we're going to tackle today. We're going to talk about tools that Linux has to offer, and believe me, there's quite a few of them. And then, of course, will I be able to find all the issues in my code with some of the techniques, profiling techniques or optimization techniques that we're going to discuss today? So those are the primary questions that I would like to pose today during our session. So let's start with the first question. Why would I optimize? So let's X-ray that little tux, and let's take a closer look at what's happening inside that embedded Linux-based system. So first statement, optimize does not necessarily mean fast. Optimized means that we are adjusting our code to perform optimally, right? So that can be a timing performance. It can be also a logical performance. The acceleration in boot time or perception of how fast our Linux system runs is oftentimes a side effect of the optimization process. As developers, we see a variety of issues with our software. We can observe sometimes slow performance. We can in certain situations run out of memory, and we're oftentimes trying to figure out why we are running out of memory. Sometimes we are writing our code, and when we deploy it on a target, we expect that it's going to do X, but for some reason it does Y and Z, but not X. And we try to oftentimes figure out what's causing that change in the execution of our software. So it's important that our code executes exactly the way we intended it to execute. And that's where the optimization tools and procedures that some of which, at least, I'm going to discuss today and show you demos with our IDE. Some of these optimization techniques are designed to assist with answering this question. Another important statement: you can optimize not only your application, you can also optimize Linux kernel code. So if you're developing a device driver, don't think that there's nothing that you can do to improve its performance. The optimization techniques, at least some of them, do apply to both. The objective of optimization, well, one is confirm that there's a problem. We need to somehow identify that there is really an issue in a system, and where does it originate? And in a typical process, in a typical optimization process, we have to start with questions before we start using any tools in our attempt to optimize our code. Why? Because random optimizations can actually further harm our code, and what's more important, they will steal away our time. So knowing exactly where the problem may be, the nature of the problem, is important before we start optimizing. So questions to ask when we are looking at this optimization problem: what makes you think that there is a performance problem in the first place? Has it been verified, or has the system ever performed in a desired manner? Are there any changes, recent changes to software, hardware, how you run your application? What are other applications in a system that execute at the same time? And how do you characterize the performance degradation? Is it a timing issue, or is it a logic issue? Does the problem only happen on your system, with your software, with your applications, or do others on your development team see exact same thing? It may be just a matter of environment that you're executing in that's causing the problem. But all these questions help us identify or narrow down a possible root cause for software performance bottleneck. And once we understand the root cause or the nature of the problem that we're trying to pinpoint, we can then start looking at which tools may help us. And this is a busy slide, but it's just the tip of the iceberg, believe me. Embedded Linux provides you with tens, if not hundreds, of different applications that are designed to help with a specific observation, with a specific functionality in your system. They can present a system call stack, so you can see what system calls are being made in your software, that there's an S trace for it. There is an L trace that helps you identify the library calls. But there's more, of course. There is a perf that's using the perf event subsystem, so profiling utilities. There is ftrace. There's an LTTng. Those are all open source based utilities that help us with profiling at the entire stack level. If we want to take a closer look at the networking, there's a whole bunch of different utilities that would probably help us. Netstat, TCP dump, if we want to take a closer look at the Ethernet traffic. We also have utilities that help us identify issues that relate to memory management. There is a VMstat or slaptop. There is top and PS to identify how the processes are executing on the CPU. So a combination of these utilities, if run by hand, should help us understand the nature of the problem that we are looking at. Okay. Today, so one more slide before we start talking about today's utilities that we're going to cover in more detail today. So profiling. That's probably one of the most common approaches to profiling, to optimizing software. By creating a profile, we get a better understanding of the execution of our software, and we can also access more information at various points in time about the software state. The profiling tools, and there's again a whole bunch of them that Linux provides, they work on the basis of snapshots. So at a timed interval, a profiling tool is going to take a snapshot, including a stack, a call stack for our application, and we'll store it somewhere in a log file, which then can be accessed by some other utilities to visualize the results. And of course, depending on utilities that we would employ, we could visualize different things. In this slide, you can see function A making a call to function B, and while executing on a CPU, at those given intervals, the stack is being stored, or a snapshot of a stack is being taken here and stored somewhere. And then whenever we make a system call, and let's say that this is a blocking system call, it can be trying to access a storage device, a hard drive. At that point in time, the process is not running on a CPU, so it's off CPU. So those samples are really meaningless, right? So there's no point in collecting. But as soon as the process that executes these functions continues, and function B returns, those samples continue to collect the information about our software. So that's the basics of how different profiling utilities work. And of course, there are different techniques of implementing this profiling approach. And we're going to talk about at least 2 techniques today. So the tools, the open source tools that we are going to experience today include tools for code coverage. And the tool that we're going to work with is called Gcov. And it's a type of a tool that requires us to instrument our application code to collect the sample. So we're going to talk more about these 2 approaches, the instrumentation and daemon-based, a bit more today. But Gcov is an instrumentation-based profiling, or for code coverage. Then we have for profiling, for proper profiling, we have the instrumentation-based approach with a utility called GProf. There's a misspell. I apologize for that. It should read GProf and not GProf. And then daemon-based, which is done through a utility or a set of tools under a common name of OProfile. For tracing, if we want to take a look at the timings and how the different processes execute in time on a given CPU, there is another toolkit called Linux Trace Toolkit New Generation, so LTTng. And we're going to take a closer look at how this works in a development environment today as well. And then for memory analysis, we're going to leverage a package called Valgrind. So all of these utilities are open source projects. And what we've done in our IDE, we leverage the open source projects, but just like in previous sessions, the focus was on the word integrated development environment. Also here, we did quite a lot of integration work to provide a seamless experience with those different utilities, with setting up a project for profiling, for tracing, and then collecting data and showcasing the data. To leverage the OProfile and LTTng, we have to prepare our targets properly. And we've created at Timesys 2 documents, and I provided direct links on the slide. Those documents describe in a very detail how to set up, how to configure our targets. Typically, that involves modifications to Linux kernel configuration. You have to select additional options for profiling and for tracing. And there are also requirements from the file system perspective. Why? Because OProfile and LTTng are daemon-based systems, which means that there not only there is a functionality built into a Linux kernel, but there is a software that runs in a file system that collects the samples, that collects the data. So to have the proper setup for profiling and tracing, appropriate adjustments have to be made to the Linux kernel and to the root file system. If you're working with Yocto, there are options that you typically would have to add into your local.conf file that are designed to bring in most of this functionality into your BSP. Okay? If you're working with factory, we also have options for this. You select those options in a config environment, and then you deploy the software on a target. So that's how easy it is. But if you'd like to learn more, I encourage you to take a closer look at these 2 documents that I've mentioned on the slide. Okay, so let's talk about TimeStorm and perspective on these different utilities that I've mentioned in the previous slides from the IDE. So the first one is code coverage. As I mentioned, it's based on a Gcov utility. Actually, not utility, but technology. And typically, you have to build your application with additional flags to get into code coverage. My apologies, I moved too fast in my slides. You have to specify flags when you compile your software. So this is why this is commonly referred to as the instrumentation approach. Why? Because without building some of that information for code coverage into your application, you will never get a profile for code coverage. The idea behind code coverage is that when you execute your software, there is a functionality that's attached to the execution that collects the samples and creates a code coverage profile log file. And that log file in the next step is copied over to a TimeStorm environment where you can take a closer look at the how the code is really being utilized, or how many times specific lines of code get to run on the CPU. And that profile also is connected to the source code with color coding. So you will very clearly see which lines never get to run and which lines get to run the most. Okay, so dark green runs the most frequently, red never gets to run, at least in that particular execution instance. It's possible that in the presence of other applications, the code coverage will be different because conditions are going to change. The code coverage is implemented in TimeStorm as a very simple process. You instrument the code, you compile the code, you deploy the code to the target, you run that code on the target, and then once you get the code coverage file back in TimeStorm, you analyze it. The viewer analyzer is integrated, of course, in the IDE. The next utility that we're going to test run today is code profiling through the GProf functionality. So open source GProf is also a feature that gets built into your application and happens at the compilation time. You have to specify different set of flags to get GProf to work. Similarly to cut coverage, GProf is going to generate a log file on the target, which gets copied to a TimeStorm. And in TimeStorm, GProf also is going to create a local information about your application. So it's going to use that in conjunction with the file that it downloads from the target with the profile data, and will create an easily browsable profiled information. The GProf approach is very easy to use, but because it's instrumentation, the timings of the profile can change, right? So what you see, or behavior that you see from an application that's not instrumented with GProf may vary from the instrumented version of the same software. But it will give you pretty much, if you're looking for the correctness of the logic inside the code, it will give you a nice overview of how the different conditions and various other C++ statements execute on a CPU. Another option for profiling, especially if we don't want to instrument our application software, especially if we are in a situation where the application is already deployed somewhere in a remote system, but we have the OProfile utilities installed, or there is an easy way to bring those OProfile utilities to the target, and the Linux kernel is properly configured for profiling. So it has the perf event subsystem built in. You can run a profile on that software. And with OProfile, because it's not associated with a specific application, you have an option of running a profile on the entire system. So not a single application, but many of them. There are two different profiling approaches that are out there. There's an event-based profiling, and then there's a counter-based profiling. If the hardware that you're working does not have performance measurement unit, it doesn't have hardware performance counters, there's always another option of enabling a timer-based profiling. The timer-based profiling typically is supported by a different version of the OProfile. So if you're using a counter-based profiling, we would recommend that you install a slightly older version of OProfile in your system. But most of the modern CPUs, they do have hardware performance counters and do support event-based profiling. So that's a good news. TimeStorm contains dedicated profiling launch configurations for not only OProfile, but the other two profiling approaches as well. And as I mentioned, if we want to profile the entire system, you have to provide to TimeStorm an uncompressed version of the Linux kernel binary with all the profiled and debug symbols in it. Not only that, that VM Linux needs to be present on the target system. So our IDE is going to upload the VM Linux to the target, enabling this way the profiling of the entire system. What will that give us? It will give us the ability to take a deeper look into our system. So if we want to take a closer look at which functions inside our Linux kernel get to run the most, the profiling with VM Linux, we can see all this. TimeStorm supports all types of profiling with OProfile. So it will support profiling of a single application, profiling over a period of time, and then profiling also with VM Linux, so with the Linux kernel profiled information. All these options that you see here are integrated with our target manager, so that when you launch applications, when you launch the profiled sessions, all that happens through launch configurations, profile launch configurations. Okay. Another approach or another type of a problem that we may encounter is running out of memory. Slow memory leaks especially are a big problem. If we have one in our system, sometimes it takes a long time before we run out of memory. So in our test scenario, we may not capture the fact that we have an issue, potential issue with our software. One way of ensuring that our application, the software that we write, handles memory properly is to run it under control of a utility called Valgrind. And there are different sub-tools that Valgrind provides. One of them is called memcheck, which is going to look for memory leaks. How does it look for memory leaks? It analyzes the software from a perspective of allocations and deallocations of that memory segment. If the deallocation is missing, Valgrind is going to flag that as a potential memory leak, giving us the very useful information about our software. Cache grind, that is a cache profiler. It performs detailed simulation of the L1, D1, and L2 caches in our CPU, so that we can accurately pinpoint the sources of cache misses in our code. And then we have Massive. It's a heap profiler. It performs detailed heap profiling by taking very regular snapshots of a program's heap. There is a viewer associated with Massive that generates a graph showing heap usage over time. And then the last one is Hellgrind. Hellgrind is a thread debugger, which helps us identify data races and multi-threaded programs. So all these utilities are currently integrated in TimeStorm, and we're going to take a closer look at them. Last utility that we're going to experience today is providing tracing capabilities. It's based on the Linux Trace Toolkit next generation. What is LTTng? Is a highly efficient full system tracing solution. It provides an integrated interface for both kernel and user space tracing. LTTng allows you to access the trace points, function tracing, CPU, PMU, counters, K-probes. It provides the ability to attach context information to events in a trace as well. It works on mainline kernels, which is great. I believe it starts with 2638 and newer. For these kernel versions, you don't require any additional patches. LTTng focuses on providing a system-wide view with detailed combined application and system-level execution traces without adding too much overhead to the traced system. So that's very important, because the moment you add overhead, you change the timing. It's very important to have the tracing capability that can capture some of the issues that we see in a deployed scenario. So with that, I'm going to switch to a live IDE. I will switch the windows real quick here. And you should now see my TimeStorm framework, one which hopefully you're familiar with by now, since this is session number 4. I have a number of applications that are preloaded in this environment. I'll start with the first one. I'll create a new one. I'll start with a C project. And in TimeStorm, we've to show you how different optimization utilities work, we have created a category called samples. Under samples in a project wizard, you can see that we have Gcov sample. So let's call it code coverage 2. And let's set it up. So wizard nicely guides us through this process. And today I have 2 targets. I have an IMX6 and IMX7, both preset for different settings, so that I can show you most of the tools that we've discussed. So I first selected a cross toolchain for IMX7, and let me complete the setup. Wizard just completed and created a project for me. Now I can right mouse click, I can build the project. The compilation is successful. I will now expand the source and the debug and source. So you can see that for code coverage, there is a file called GCNO that got generated. Why did it get generated? Well, the answer is in project properties. And as we've mentioned, code coverage is done through instrumentation. So I'm going to expect that there are certain flags that have been used by the compiler. And so I navigated to properties for my project settings, and under tools settings, you can see that I have these 2 flags, ftest coverage and fprofile arcs. You can also select optimization, debugging. No, that's where they are. But you can always add those flags for your application manually. So you can specify this ftest coverage and fprofile arcs right in here. You can type them in. So this will apply to any application that you want to identify the usage, or which lines run get to run on the CPU and which ones don't. Okay, so that's what caused the GCNO to be generated. So now, using the context menu, there is a dedicated group of actions under TimeStorm profiling tools, and the first one is called code coverage. So I'm going to select that. And for code coverage, I already have the entry made here for my CC2. So TimeStorm, again, tries to assist as much as possible. I can specify here program arguments. And for target, I'm going to execute it on IMX7. Okay, so apply and profile. So watch closely here. No space left on device. Interesting. So let's see what's happening. Oh, that's because I've run some traces here. Okay, we'll make space. LTTng traces. And let's try to run it again. Code coverage and profile. Okay, and you can see that there is another file called GCDA that popped up here. So that file got generated on the target, and TimeStorm copied it over to this project tree. So all I do is double click on it, and that's how I start the code coverage viewer. Don't have to change anything here. Say OK, and now I have the application color coded. So it's a very simplistic application. This code coverage works nicely with multi-files, multi-directories, and it will show you which code never gets to run, which line of code gets to run the most on a CPU. Okay, so that's code coverage. Second one is going to be C project sample applications, and we're going to do GProf, so profiling through instrumentation. I'm going to call it GP2. Same exact setup of the project as in a previous exercise. I'm going to use IMX6 for it as well. I'm sorry, IMX7. And let's compile. Okay, let's open up the source code to take a closer look. Okay, so no color coding of any kind here. Now build the project. Let's close the Gcov. GP2 is built. Now I'm going to expand again all the directories, and we're going to look for occurrence of the file called gmon.out. So profiling tools, GProf. There's a different flag for profiling with GProf. I'm going to select the target, IMX7, arguments, 1000, apply, and profile. So the application runs at this point on our target, 1000 iteration loops, and you can see a gmon.out popped out in our code. Just like with code coverage, we double click it, and profile viewer starts. Now I can expand, and I can see very clearly that there are two functions, function A and function B. Here's function B. From the profile, and 1000 samples, that's how many calls. Samples is 112 and 445 collected on function B. So most of the CPU time was spent in function B. If I expand function B, 42% is spent on this line. And I double clicked it, and you can see that it's a while loop. So, this is 36% spent on this addition here. So if I have bad logic in my code, I can very clearly identify where the CPU is really using active cycles. Okay, so that's profiling number 2. Now we're going to use the existing OP2. It's an application that was compiled earlier. There's no instrumentation of any kind in this software. I will open up the software to show you that it's just a regular fast multiply, slow multiply, simple C program. And now we're going to profile it, but for OProfile, I have an IMX6 setup. So we're going to select OProfile. And TimeStorm communicates already at this early stage with the target. And I can pick here from the targets that I want. Every single time I select a different target, TimeStorm is going to query the target about its capability to profile. Why? Because those kernel options that we discussed earlier must be present in the kernel. Okay, so that's what selecting the target here does. It verifies that the kernel is configured properly and that there are utilities installed in the root file system. So it looks like our IMX6 is ready for profiling. So now I'm going to call it LPS1 session 2. For the profiling, I'm going to profile my application software. And so the OP2 application, and I'm going to delay the startup by 4 seconds. But you can see here that I can profile also the entire system timed based, and I can specify for how many seconds or minutes I want the profiler to collect the samples from the target. That would collect the samples not only from my application, but also from other programs. If I want to, in addition, collect information about the Linux kernel itself, I would have to uncheck this No VM Linux and browse to a VM Linux file on my PC on a development system. TimeStorm will take care of uploading that VM Linux to the target. By default, TimeStorm is going to enable default events to trace. You have, of course, ability to change that as well. So at this point, I have just started the application. You can see here that waiting for profile startup delay 4 seconds, and now it collects the data about our software. So that's going to take a little bit because we also have 1,000 loops, but that's going to come back very soon. Okay, you can see actually in TimeStorm that I have a previous OProfile run, and the event on which the profile run was the CPU cycles, right? So quite frequently the samples have been collected from the running application and from the running system. So TimeStorm is importing profile data. Notice I'm not leaving the IDE. Everything happened here. So now I just double-click at the profile information output. I can expand the OP2. You can see that OP2 was, or the profile collected most of its samples in the OP2 application. I expand that, and I can see slow multiply is hogging the CPU. I expand that, and there are specific line numbers, which TimeStorm is taking us to. And the color coding on the left-hand side also tells us the utilization of that specific line, right? So 68% of the time CPU has spent in this for loop in a slow multiply function. Okay. So this is a nice way of, again, navigating through the code. If I scroll up or down, the profile there gets reflected for the entire file. Okay. So that's profiling. Now let's close the GProf. Let's close all those other files so that we are not bothered by any other output. Clean the console. We're ready for Valgrind. So with Valgrind, we want to take a look at specific memory issues. And we're going to select a new project, samples, Valgrind, and I'm going to call it MM2. Set up project quickly. I'm going to perform Valgrind on IMX6. I have MM2 here. We're going to compile it. There's no instrumentation done in this code, but the way Valgrind works is the application must be executed under the control of the Valgrind utility, which must be present on the target. So it's important to have Valgrind installed on the target system. So now I'm starting a profiling based on Valgrind. Target IMX6, Valgrind options. Here's where I can select memcheck, massive, and those other utilities. Let's start with memcheck first. Apply and profile. So I think that my target may be in an unhealthy state. So I don't want to necessarily solve this problem right now, but let's do first maybe LTTng. For LTTng, we have this button here that allows us to navigate to TimeStorm tracing tools configuration. And I can click on any of these and then select a target that's configured for tracing. My IMX7 should be configured for tracing. Yes, it is. I can create a new session or, well, let's create a new session. That's just going to take a moment. L5. OK. And then all events. Apply and launch the LTTng. So that started to collect the tracing information on a target. We are tracing IMX7, so I'm going to do a PS here, ls, and maybe ls mod, ps again. So a couple of functions that I've executed as the tracer is collecting the data on the target. So now I'm going to stop this, and I'm going to import no such file directory. Well, because I don't have space probably on the target. Let's get rid of everything here, and let's do it again. ls ps ls mod yes. Okay. Stop and import. I'm hitting some problems here with the quota on the target, quota of space, which prevents the trace from being created, but not to worry. That's why we call it the cooking show. I have two other runs. I can double click on one of these runs and show you the output from one of the executions. So this is a collected trace from the IMX7, and it's still at this point reading in all the samples into the IDE. I can zoom in on the specific time here. You can see in this view here that I have all the processes that have been executing in the system listed here. So I can scroll down or up to a specific occurrence, and different events are also captured. So there should be a RCUs. And I can zoom in on a timeline. I can scroll up and down, I can identify why the preemption happened. Like in this case, there's an RCU preempt. So there is, we see why specific context switch happened for a specific process. And there are not only system processes, there are also user space processes that this utility captures. Okay. And similarly to this, I've pre-cooked OProfile. No, not OProfile. The Valgrind, maybe I have not. But let's try the other utility before we give up on this target. Okay, let's try a Valgrind, or actually cache grind. Apply profile. Okay, it's working on IMX7. Oh, it did come back. So here we have the utilization of different caches. And I can expand to see for a specific software here how the cache was used. So in my MM2, I have thread function. And if you do a mouse over, it will tell you what this represents. Instruction fetch miss, data read access, L1 read miss, and so on. So I can clearly see where the caching is failing on my application. But let's give it a shot again with the other utilities of Valgrind. So we tried cache. Let's try the heap profiler. We have a heap profiled. So here we can see different aspects of the total heap, useful heap, and extra heap. So we can see how many bytes of heap have been used by our MM2 application. One last try of the mem check. Yep. Looks like my IMX7 got into a better state, which is good. And we can see here that there is a memory leak that comes from this malloc. So there is no associated, actually there are two. There's this one, and then there's this one. And there's no deallocation of variable x anywhere in here. So that's where our memory leak originates. Okay. So that's it for today. I'm already over my budgeted time. Thank you very much for your attention. And let's take a look at the questions. Yep. So one of the questions that I see here is, for these tools, do you find that they are fairly non-intrusive? Or do they impact the behavior of the system? So any instrumentation utilities that I showed you, GProf, Gcov, they may alter the behavior of the overall system. Same with Valgrind. Valgrind is very heavy on the system, and because our application runs under the control of the Valgrind, and Valgrind uses a lot of memory as well, the behavior of the overall system is going to change. So these tools are very useful when you want to identify bottlenecks that relate to correctness of the code. If you would like to, if you're more interested in timing behavior or a profile information that shows over time without the instrumentation, OProfile and LTTng are very good options. They are very lightweight, and they typically don't carry too much overhead. So that's the trade-off.
Great. Any more questions, Maciej? Did we get any more? I don't see any other ones. I don't know. Did you receive anything in emails? Any questions?
Well, so one question that I received was actually very similar to the question that was asked today, but it was specific about Valgrind. If Valgrind is heavy on target system resources or not, and the answer is it is pretty heavy on target resources. So more complex the application becomes, more resources Valgrind is going to require to provide us with appropriate information.
Great, thanks, Maciej. This was really a good session. A lot of good information about why we would want to optimize our code, optimization techniques, and interesting how TimeStorm, using TimeStorm, one tool for all of the optimizations that you can do, certainly helps to accelerate development. We've covered a lot of information in the last 4 weeks, and I hope everyone has enjoyed these sessions and had an opportunity to register to use all of the features of TimeStorm. You can do so at linuxlink.timesys.com, and you'll be able to use the fully featured TimeStorm for 30 days. So check it out. And before I sign off, or before we sign off, actually, I also want to let you know that we uploaded another video to our TimeStorm IDE playlist. The video is titled Profiling Through Instrumentation with TimeStorm, so it certainly relates to today's session, so you're going to want to check that out. Following this session, at any time, please feel free to email me. You can reply to any of the emails that you've received. Send me any questions. I will forward them to Maciej, either he or myself. One of us will get back to you with answers to your questions. Or you can simply send an email to sales@timesys.com. Both Maciej and I received those emails as well. So if you misplaced my email address, you can certainly use that one. And finally, we will soon be announcing another series, which will focus on managing security and updates of your custom Linux OS. So keep an eye out on your inbox, as well as check out our website for details. They'll be coming soon, within the next week or so. I believe that's everything. So Maciej, thank you again. And on behalf of Maciej and myself, I want to thank you for being with us today and for this entire series. We hope you have a good day, and we really look forward to seeing you again online for our next series. Thanks, everyone.
Thank you.